You know, when you think about concrete, you probably think gray, boring, heavy. But what if I told you that the most common material on Earth, besides water, is secretly becoming one of our most advanced? What if it's the key to solving some of our biggest climate problems?
And that's not some far-off sci-fi dream. It is happening right now. In this explainer, we're going to dive into some amazing research that treats concrete less like, well, a rock, and more like a programmable material. Seriously, think of it like writing code, but for chemistry. You can literally design it for whatever you need. Maybe you need incredible strength, or maybe you need it to be lighter than wood. Yeah, you heard that right.
Okay, so to really get why these solutions are such a big deal, we got to understand the problem we're up against. And with our buildings, it's kind of like a two-headed monster. First, there's the massive carbon footprint of just making the stuff. And then there's the crazy amount of energy our buildings chew through just for heating and cooling. So yeah, it's a real double whammy for the planet. We're pumping out massive amounts of CO2 just to cook up the cement, and then the buildings we make with it just guzzle energy for decades. It's like we're fighting a war on two fronts, the pollution from making it and the waste from using it. All right, let's talk solutions. The first one is a game changer. It goes right after that giant carbon footprint. And we're not talking about some tiny tweak here. No, this is about completely swapping out the single worst offender in the whole recipe. And this is where it gets really clever. It's called alkali activated concrete, or AAC for short. Basically, it throws out the traditional cement and instead uses industrial waste products. We're talking about fly ash from coal plants and slag from steel mills. It's high-tech recycling. See, the whole reason normal cement is so bad is you have to cook limestone at insane temperatures, over 1400 degrees Celsius, which just dumps CO2 into the air. AAC just skips that whole carbon-heavy step. Pretty smart, right?
Okay, but there's always a catch, isn't there? For an engineer to actually build a skyscraper with this stuff, they can't just cross their fingers and hope for the best. They need to know, with total certainty, that the concrete will be exactly as strong as they designed it to be. And bridging that gap, from a cool lab experiment to something you can rely on in the real world, that's been the huge roadblock. Well, until now.
And this is the breakthrough. This 8-step guide is basically the recipe book for green concrete. It takes all that super complex chemistry and boils it down into a simple, reliable process. Now, any engineer on any job site can follow the steps and get a predictable, high-performance mix. This is the thing that takes AAC from a cool idea in a lab and makes it a real-world, scalable solution. All right, so that recipe book gives us a way to build a strong, green skeleton for our buildings. Awesome. But what about that other head of the monster, all that wasted energy? To tackle that, scientists went in a completely different direction. Instead of programming concrete for strength, they programmed it to be mostly air. Think of it like a web of tiny, strong air bubbles. This really shows you the new way of thinking, right? On one hand, you've got your normal, heavy-duty concrete, but on the other, you have this stuff, cementitious foam. The easiest way to think about it is they whip it up with a foaming agent, kind of like making meringue for a cake. You end up with this rigid, incredibly light material whose only job is to trap air and act as a fantastic insulator. Now, just how light are we talking? Around 180 kilograms per cubic meter. I know, that's just a number, but get this. A solid block of this stuff would be lighter than a block of pine wood the same size. That's insane. It's not even in the same league as traditional concrete. And this number here, that's the one that matters for insulation. It's called thermal conductivity. You don't need to remember the name. Just know that it tells you how good a material is at stopping heat. The lower the number, the better the insulation. And this value is really, really good. It makes it a fantastic insulator. And the best part, unlike a lot of other insulation materials, it doesn't burn. And this is where things get really weird for a material we call concrete. It's incredibly ductile, so if you put it under a ton of pressure, it doesn't crack and shatter like you'd expect. Instead, it squishes. Yeah, it squishes down like a hard sponge. It can actually deform about 15 times more than regular concrete before it gives up. Wild, right? Okay, so we've got two amazing new materials. But as any engineer will tell you, there's no such thing as a free lunch. Every innovation has its trade-offs. So let's get real for a minute and look at the practical side of things. Where does this stuff make sense, and what are the limits? So let's talk money. When it comes to the strong, green concrete, the story is pretty interesting. For your average job, like a house foundation or a sidewalk, the old school stuff is still a little cheaper. But when you need the really heavy-duty, high-strength concrete, we're talking skyscrapers, massive bridges,
That's where the green AAC is already neck and neck on price.
And yeah, the research totally confirms this. The sweet spot, for now, is in those big, high-performance projects. That's where it really shines. But, as things like carbon taxes become more common, you can bet this green alternative is going to start looking a lot more attractive for just about everything.
And what about our ultralight foam? Well, its biggest weakness is actually its superpower, that squishiness. When it fails, it doesn't crack, it just crushes down. So it's pretty obvious you can't build a house out of it, right? It's a total specialist. Its job is insulation, period. It's not there to hold the roof up.
So let's bring it all together. We have a strong, green concrete for the structure and a super light, fireproof foam for insulation. What does that actually mean for the future for the cities we're all going to be living in?
Here's the real shift in thinking. We're moving away from thinking of concrete as this one-size-fits-all brute force material. Instead, think of it as a toolkit. A builder in the future can pick the right tool for the job. They'll use the strong, green AAC for the skeleton of the building and then wrap that skeleton in the ultralight foam. The result? A building that is way more sustainable to build and way cheaper and more comfortable to actually live in.
We used to think of concrete as ancient and unchanging, but what this research shows is that it's becoming one of our most advanced materials. It's now a high-tech, programmable material. So that leaves us with a pretty exciting question. What problems will we engineer it to solve next? Thanks for watching.